So what does it mean for two matrices to be equal? The same is true for vectors as well. So two matrices A and B, denoted by the corresponding AJK and BJK elements, are the same if and only if they have the same size, they have to have the same size, and the corresponding elements are the same. So, for example, well, 1, 2, 3, 4 is the same as well 1, 2, 3, 4, right? But this is not. But if I give you 1, 2, 3, 4, 5, 6, this is not equal to 1, 2, 3, 4, 5, 6. Even though it has the same elements, this has 2 rows, this has 3 rows, this has 3 columns, this has 2 columns. So they're not equal. They are different. Okay. Um, so the sums of two matrices are AJK and BJK is denoted in is done by taking the corresponding element-wise summation. So, for example, suppose someone gives you 1, 2, 3, 4, and asks you to add that to 4, 5, 6, 7. What do? You take the first element, 1 comma 1 element from both, and 1 plus 4, the 2 comma 1 comma 2 element from both, so 2 plus 5, 3 plus 6, 4 plus 7, and that is therefore 5, 7, 9, 11, right? Matrices of different sizes cannot be added. Keep that in mind. The scalar multiplication, so multiplication by a number is if someone gives you a matrix A and asks you to multiply it by a scalar C, then it's basically the same as multiplying each element of the matrix by the scalar C. So if someone says do 2 times 1, 2, 3, 4, that is the same as doing 2 times 1, 2 times 2, 2 times 3, 2 times 4, which is, of course, 2, 4, 6, 8. By the way, the same can also be done where the elements are things like 2 times A, B, X, A plus X would then be 2A, 2B, 2X, 2A plus 2X. Yeah? So there's nothing fundamentally complicated about that. What are the geometric meanings of these things? So it's easier to see the geometric meanings for vectors. So if someone gives you a vector, for example, suppose someone gives you a vector 1, comma 2. So 1, comma 2, this is the vector 1, comma 2, and also gives you the vector 2, comma 1. This is 2, comma 1. Then 1, comma 2, so 1, comma 2 plus 2, comma 1, 2, comma, what is the typo? 2, comma 1 is, of course, 3, comma 3, right? Which is the same as adding, so adding 2 to 1, so getting 3, and then 1 to 2, and getting 3 in this direction. So it's like if you've probably seen this when you've studied vectors. So I take one vector, and then from the ending point of this vector, I take the other vector. I shift this vector over here. I move along. I move one step along the x-axis, 2 steps along the y-axis, and therefore the summation of these two vectors, the summation of the 1, comma 2 vector and the 2, comma 1 vector, is the summation of moving 2 steps along the x-axis and then 1 step along the x-axis, and moving 1 step along the y-axis and then moving 2 steps along the y-axis, and that's how I get 3, comma 3, right? That's the geometric meaning of addition of vectors. The geometric meaning of scalar multiplication of a vector is, so suppose someone gives me 1, comma 2, this is the, 2, comma 1, and someone says multiply this by 2. So that's like saying make this vector twice as long. So then I'll end up with a vector 4, comma 2, okay? Because that's the same as making the x-axis component twice as long and the y-axis component twice as long. So the x-axis component now becomes 4, the y-axis component now becomes 2. So that's the geometric meaning of addition and scalar multiplication of vectors. Um, the geometric meaning of addition and scalar multiplication of matrices is more complicated, and we'll discuss this shortly.